Okay, so in class we talked about the y displacement of a string that has a wave on it is equal to the amplitude of the wave times the cosine of kx minus omega t. And k is the wave number, which is 2 pi over lambda, and omega is the rotational frequency, or 2 pi times the periodic frequency. We also have, remember, frequency is 1 over the period. What else do we know? We know wave speed is equal to lambda times frequency. So this section is page 476 and 477, and it's asking to calculate the acceleration and velocity of this vibrating string, and it's going to be a function of x and t. So if you think about, you've got some string that has a wave on it. So let's say it looks something like this. So we haven't reflected anything yet. We're not talking about reflected rays, so it might be good to just get rid of this and just think of it as a string that's vibrating. And what we get is, this wave travels downstream, and the velocity is, the wave velocity is equal to the square root of F over mu, where F is the force tension in newtons and mu is the mass per unit length. So you could figure out what lambda is by taking solving for lambda from this equation. It would be V over F, where V is related to how much tension is in the string and mass per unit length. Anyway, so this thing's moving down at any instant of time t. It's a sine wave or cosine wave. It just propagates in the x direction according to this relationship. Okay, so if we want to find the velocity in the y direction, so this is the y coordinate, it's also a function of x and t. And so what we do is we take the derivative of the y displacement as a function of t with respect to t. So we, instead of using straight derivatives, we use partial derivatives, because this function here is a function of both x and t. But we're just going to treat x as if it's a constant. So if you think about this from a calculus standpoint, we'd let u of x equal k, or actually u of x and t. In this case, u of x and t is kx minus omega t. So if we reduce the chain rule, you get u prime, or in this case, we have to be more specific, the partial of u with respect to t of this function x and t. All we do is take the derivative with respect to t. This is treated as a constant, so there you get 0, and then the derivative of this is just omega, because the derivative of t with respect to t is 1, so you get omega. So v sub y is just a, the amplitude from the original equation, times omega times the sine of kx minus omega t. So the partial derivative doesn't change the argument. It only affects the chain rule part, and there's actually a negative sign here, so it's negative. So it's negative a omega sine kx minus omega t. Actually, the derivative of the cosine is a sine, so there's two negatives here. So I actually get a negative because the derivative of the sine, cosine is negative sine, and you get a negative. So ultimately it ends up being positive, so it just becomes a omega sine kx minus omega t. So that's the y velocity in the y direction. And then to find the acceleration in the y direction, it's the partial of v of x, v sub y, of x and t with respect to t. So the same kind of thing happens. We take the derivative, in this case of the sine, which is the cosine. You do get a negative. This negative shows up again. So you get negative from the chain rule here. You have the amplitude still. Instead of omega, you get omega squared, because you get that happening again here. And the derivative of the sine is the cosine. So you get cosine of kx minus omega t. So that's the acceleration in the y direction. So you're going to get the maximum. It turns out you get the maximum velocity when the displacement is 0. It's kind of like with the spring mass system. You know, you got this string that's stretched, and it's stretched upward. When it comes down, it's going to flatten out. This point where it's flat will have the maximum velocity. It'll have 0 acceleration. So at this midpoint, when it comes down, it's going to be 0 acceleration, 0 displacement, and maximum velocity. Then you get over here and you get the maximum displacement in the negative direction. The acceleration is going to be upward because it's got this stretch that wants to pull it back to its equilibrium position. You can almost see the same kind of the analogy between spring mass and this wave on a string, because if you let this thing go all the way down to the bottom, it's like having this stretch to the bottom. Once this mass goes to this maximum displacement, it's got an acceleration that's pulling it up. It's got a 0 velocity. Now if you take the derivative, the second derivative of y, or v, of x and t with respect to, so this is the second derivative of v and x and t with respect to x instead of with respect to t, what you'll end up getting is you will get, instead of this factor of negative omega, is you'll get this factor of k. You'll still get a negative because you get this second derivative situation. So you get negative k squared a times the cosine of kx minus omega t. Now if you take the ratio of the second derivative of y, so this should be actually y, not v, sorry. This should be y, second derivative of y. So if you take the ratio of the second derivative of y with respect to t divided by the second derivative of y of x and t with respect to x, so what do we end up with there? So this is the top, negative a omega squared cosine of kx minus omega t, and if you divide that by this, you get negative a k squared cosine of kx minus omega t. So the negatives cancel out, the a's cancel out, the cosines cancel out, and you're just left with omega squared over k squared. But omega is 2 pi f, so you get 2 pi f squared, and k is 2 pi over lambda squared. So the 2 pi's cancel out, 2 pi squared cancel out, and you're and then this comes to the numerator because you take the reciprocal of that, so you get lambda f quantity squared, and that is equal, lambda times f is the velocity, so they give v squared. Or you can rewrite it in this form, which says the second derivative of y of x of t, y of x and t with respect to x squared is equal to 1 over v squared times the second partial of v y, sorry, second partial of y of x and t with respect to t squared. And this is called the wave equation. So anytime you have a wave, or anytime you end up with this relationship between the derivative with the second derivative with respect to x and the second derivative with respect to time, then you can assume that the function or the behavior is going to be periodic in some nature. It doesn't have to be sinusoidal, it just has to be periodic. Okay, so that's the basic idea here. So I'm going to assign 2 homework problems that take into account all the things that we've learned relative to waves. There's an example in the book that you can look at to help you guide you before you try these without looking at the video. And let me see if I can find the equation number. So I think it's 15.2 on page 476. Okay, so use that as a kind of a guide. Look through that equation, look through that problem, and then I'll give you these. So the 2 problems that I'm going to assign are the ones that are, say, calculus spaced in the back of this section. So there's, let's see if I can find it here. Okay, I think I found it here. Yeah, so these are the two problems. It's 15.41 and 15.49. I specifically chose them, they're odd, so I can check my answer when I work through it.